Good morning, everyone. So, I'm Jeetendra Sonar, and I'm from the IBM Storage Engineering team back in Pune, India. We have been working on implementing ISER over RDMA for over a year now, and the idea of this presentation is kind of to bring up the challenges that we faced while developing the application. This paper was originally submitted by Subhajit and Tej, who are my colleagues, and I'm kind of representing them today because they were not able to travel. So please feel free to ask questions at the end of the sessions, but if I'm not able to answer, I will get you the answer later. With that, so this is the agenda. It's kind of split between the introduction and the challenges section. So in the introduction, I'll try to set a bit of context as to what our application is, its capabilities, and what we are trying to do with ISER on our application. And I'll also cover a very high overview or the architecture of our application. And then in the challenges, I'm kind of highlighting some of the key challenges that we faced while developing this application. And in the end, I would like to share some conclusion based on our experiences developing this application. So with that, let's try to understand what is SVC. So SVC, as it's called as SAN volume control or IBM Spectrum Virtualize. So it's a block storage virtualization application. What it means is, it virtualizes heterogeneous storages for the hosts. So it kind of pools storages from different vendors into managed disks and then provisions them to the host. So if you look at the diagram, it kind of sits in between the hosts and the actual block storage targets. Now there are two variants of the application. So one is just a virtualizer, which does not have any disk space of its own. And the other variant is essentially a virtualizer which has SAS or flash disk attached to it. Now this application originally was using fiber channel and FCOE to be able to provide the virtualization and host attached capabilities. And we started working, as I mentioned, implementing ISER a year ago to be able to leverage the advantages that are offered by RDMA. Now, the primary use case that we are targeting for ISER in our first release is essentially doing clustering. So our application is clustered for high availability, and we want a low latency network to be able to cluster our nodes together. And ISER was our choice to be able to implement that capability. Now, so far as the number of nodes are concerned, so we kind of scale up to 8 nodes in a cluster. And the current ISER supported number of ports per node is 8. So essentially users can have segregated or dedicated ports for host attachment, backend attachment, as well as clustering. We also support both RoCE and iWARP protocol with ISER, and support all the bandwidths right from 10 gigabit to 100 gigabits. So that's a brief overview of the application. So let's take a look at the architecture. And I've kind of listed some of the characteristics of our architecture. So if you look at the diagram, our application sits in the user space, while the ISER and iSCSI drivers are in the kernel space. We have a lockless architecture, and we have implemented per CPU port handling. What it means is, the IO ports are distributed across the CPUs that are available on the system. However, we tie the processing of a particular port to a CPU. So that's mainly done because we want to operate in a polling mode. So all the IO transactions as well as connection management is polled by the application over a particular CPU. Then, as I mentioned earlier, we support both RoCE and iWARP with ISER. And we have tried implementing a vendor-independent architecture So essentially, we can support all the major RDMA vendors available there in the market. And last but not the least, we are heavily dependent on the OFED kernel iWARPs to be able to implement or use RDMA for our transactions. With that, let's take a look at some of the key challenges. Now, of course, I mean, we have been just working for a year, and I'm kind of highlighting the challenges and some of the workarounds that we've used, but there will be better methods to handle them, and we'd like to hear from you folks if you know of better methods that can handle the problems that we have faced. So the first kind of challenge that we faced was with QPair States. Now, since it is a clustering, or it's a block storage application which is kind of clustered across nodes, we are very sensitive to the timeouts during network outage. So our goal was to control the number of retries and retry timeouts during network outage. But the actual behavior that we saw was that the QPair transition differs across RoCE and iWARP. Specifically, iWARP does not support the send-queue drain state. And during our implementation, we were trying to transition it to that state to be able to change the QPair attributes. Our expectation is that the IB modify QP API must transition the QPair states as per the diagram that is shown there on the right. And all state transition must be supported irrespective of whether it is RoCE or iWARP. So the workaround, I mean, we couldn't find any workaround using the kernel iWARPs to handle this problem. So currently we are working with some vendor-specific method to be able to control the timeouts. So the next challenge that we faced with the RDMA disconnect behavior. Now, as I'm showing in the diagram there, this was specifically seen when a peer port on the network has an issue or gets disconnected. Now, we were not able to free the QPair until we received the RDMA disconnected event, and we couldn't find a way to control the timeout period for this event as well. So the actual behavior that we saw was the link down on peer system caused disconnect event to be received after a long delay. And just to give a rough example, for RoCE we saw that it is received after 100 seconds, and for iWARP it was received approximately after 70 seconds. Also, there's no standard mechanism that we were able to find in order to control these timeouts. Now, our expectation is that the RDMA disconnect event must exhibit uniform timeouts across RoCE and iWARP, and the timeout period for the disconnect must be configurable. So there should be a way available in the WARPs API to be able to configure those timeouts. Again, for this particular issue, we are evaluating vendor-specific mechanism to tune the connection management timeout. The next challenge that we faced was with the RDMA connection management. So, as I had mentioned, during the architecture slides, so we kind of work in the per CPU polling mode for the I/O as well as connection management for other protocols. So our expectation was that even with ISER, we should be able to kind of work in a similar model wherein we can do a polling for data path completion as well as connection management events. However, we found that there is no mechanism to poll for the connection management event, and the RDMA connection events use interrupts, which we do not like that much. So the also from the applications perspective, so there is no control over which CPU the polling of connection management events comes on. Now, since we kind of tie the processing of an I/O port to a CPU, we kind of expect that everything, including the interrupt, should come on the CPU. But in this case, it was received on the other CPUs which are tied to some of the other ports. Now, our expectation is that similar to the I/O transactions, for connection management event as well, there should be some sort of a queue mechanism which our application can keep queuing whenever there is a connect or disconnect event. And the workaround was, since it uses interrupt, we have to use logs, which is kind of adding to the I/O latency a little bit. The next challenge we faced was with the large DMA memory allocation. So in the table, I'm showing kind of a sample requirement in terms of memory required by the send queue, receive queue, and completion queue for our application. And our observation was that allocation of large chunks of DMA memory during the session establishment fails. Now, this is because of the reason that when SVC application initializes, it kind of claims the majority of the memory for caching. So it kind of caches the I/O, and it needs a lot of memory to be able to do that function. And in the current mechanism, we observed that when the QPair is created, the verbs use kmalloc based allocation, which is failing because the kernel memory is kind of very limited. Now, our expectation is that the verb mechanism or the verb API should provide a means to allocate DMAble memory from a pre-allocated memory pool. For example, in the IB alloc CQ API and IB create QP API. So we can do a pre-allocation of memory that can be used by the RDMA devices while the application is initializing, and then we need that support in the API to be able to allocate memory from the pre-allocated pool rather than the kernel memory. Now, we couldn't find any workaround using the APIs for this solution. Hence, we had to modify the iWARP and RoCE drivers to use pre-allocated memory pools. The next one was with querying and modifying QPair attributes. So again, our application is kind of very sensitive to timeouts, and we wanted to have an ability to control QPair parameters, especially for error recovery. We were unable to kind of get and set QPair parameters. Specifically with iWARP, we found that some of the parameters are not supported, which are defined, rather modifying and querying of the parameters is not supported, which is defined in the IBQP attribute structure. For example, the RNR retry, so we were not able to kind of control the RNR retry timeout. Now, our expectation is that the IB query QP and modify QP should behave as documented, and if there are some differences between parameters for iWARP and RoCE, they must be documented. Again, for this issue, we are kind of working with vendor-specific mechanism to solve our problems. And the last challenge is with the querying the RDMA device list present in the system. Now, we want to essentially query the devices, RDMA devices that are present in the system while our ISR kernel driver is initialized, so that we can do better resource allocation depending on the number of devices that are present in the system. However, we couldn't find a kernel verb API to be able to solve this, or to be able to query the device list of the RDMA adapters that are present in the system. So in the current mechanism, RDMA devices are available only after connection request is established by the CM event handler. So our expectation is that there should be a kernel verb equivalent of IBV get devices available, so that we can do better resource allocation. To conclude, our initial indications of performance, benchmarking show that the ICER performance is comparable to FC, which is excellent and which we like. We believe that ICER presents an opportunity for high-performance flash-based Ethernet data center. Although in the IO path we didn't face much of an issue, but specifically error recovery and handling is a bit of troublesome. We think that mass adoption of OFED Stack by storage vendors require a little bit of more work. Specifically, the iWARP is not completely protocol independent, and some work is needed to be able to make it independent of the protocols that are there. We also think that there should be a proper documentation of RoCE versus iWARP specific differences, so that we can define our architecture based on the documentation available. And then we think that there is a need for a resource allocation timeout value similar to RATOE equivalent in fiber channel. And we also feel that same requirements will be applicable to NVMe over Fabric as well. And lastly, as I was mentioning it earlier, we are seeking for a forum to address this requirement so that the applications or the APIs can be better tuned to suit for storage application. So with that, thank you very much. Are there any questions that I can take? Sure.
That's maybe a simple question. Question is, if you can't use kmalloc, why are you not using vmalloc, which is giving you as much as you want?
You can't use vmalloc
For what?
for the SRQs.
Okay.
For the Q rings, they have to be contiguous.
Okay. Thank you.
Sorry, Bernard was asking why can't you use vmalloc to allocate the queues in the kernel, and the answer is they have to be DMA contiguous for the hardware to use them.
Yeah.
Yeah, DMA contiguous. It is DMA-able memory, right? Yes, because it's the memory that the adapter is reading the work queue entries out of. So my question was, on your last slide there, you said you were looking for a forum.
Yep.
I think whenever you want something changed in the Linux kernel, the appropriate forum is one of the various Linux kernel mailing lists. So send a patch.
Absolutely. I mean, yeah.
All right.
We are very happy to do that, and definitely, I'll talk to you offline as well and see how we can do that.
Okay. Yeah. Some of the stuff is sort of difficult, but the other stuff, definitely documentation and things, is very, very easy.
Sure.
Very easy to do. All right. Thank you.
Okay. All right. Any questions?
So we've run into problems with these various timeout tunables not being exposed, and so this is in, comes back in Lustre and MPI and all sorts of areas. So I don't know, I have a common experience there, and it's been that way for a long time.
Okay.
So is it ever going to change?
No, as I mentioned earlier, I mean, these are very specific to our storage applications. So yeah, if there's a way to kind of handle those, then we'd love to do that.
Hi. Do you know which parameter did you change in SQD? You mentioned you changed QP attribute.
Yeah, so specifically the retry and retry timeout. So that is what we were trying to kind of modify and control. But with RoCE, or rather with iWARP, we observed that the SQD, the QPair doesn't transition to the SQD state. And that's why any changes to the parameter that we wanted to do was failing.
I see. So retry timeout. Retry timeout, that's what the...
Okay, yeah, retry timeouts.
Thanks.
Yeah.
Yeah, regarding the timeouts, think one of the differences that you see between RoCE and Infiniband is that, RoCE and iWARP is that okay. In the timeout processing in Infiniband networks, there is this notion of the max latency in the fabric that comes from DSM. So that pertains to Infiniband. In RoCE and iWARP, probably they are hard-coded. We do have multiple retries in several layers. I think that we have the MAD layer doing retries, we have the CN doing retries. All these add up, and that's how we reach these number of counts. Could be the solution that we need to have more tunables regarding each level.
I agree.
So again, let's discuss the mailing lists and patches.
Sure. Right. Anything else? All right. Thank you very much. Thanks for this opportunity for presenting.